Alright guys, so for this next video, what we're going to do is we're going to start off from where we left off in the last video, where we did an inverter simulation with a DC analysis, and then today what we're going to do is we're going to show how you can convert this schematic, or really any schematic, into a symbol to make it easier to use in more complex designs, and then also how you can do transient simulations, things like that, to help make more robust, more flexible, and make it easier to, like I said, make more complex designs without actually having to manually place and modify every single transistor. So if you haven't watched the previous video, maybe want to go back and watch that just to learn how we got to this point. But we're pretty much just going to start off from this very simple inverter that we had in the last video that's not optimized. The widths aren't optimized to where they're matched and the response is symmetric, but it's going to allow us to modify this to show you how to make a symbol and how to do transient simulations and things of that nature. So what we can see here is that we have a very simple inverter schematic, and if we wanted to, we could just come here, select everything, copy it, and then paste it a little further on down the line in order to make two inverters back to back, so something like a buffer. But that can get pretty cumbersome. It can get pretty complicated because now if you have, let's say, we start off with 2 transistors, now we have 4. If we're doing a fan-out 4 design, which is 5 inverters, then we're going to have 10. And then, of course, this is not super complex because this is just an inverter. But if you're trying to build something very complex like an ALU or a RISC CPU, then that can become very complex very quickly. So what we're going to do is we're just going to see how to start off with a symbol, how we can pass parameters so that we can take this symbol and modify the internal components, and then excuse me, then what we're going to do is we're going to look at transient simulations. So starting off just from this inverter design that we have here, in order to make this a symbol, we have to kind of clean it up a little bit first to make it a little bit more general. So what you'll notice is, like, these symbols here, these transistor symbols, they all have pins. So they have 4 pins here: body, source, drain, and gate. So an inverter, we're only going to need 2 pins, an input and an output, but we can't really have these voltage sources inside of our design because we want our symbols to reflect what we can have on chip, and then we can use these symbols to test them with ideal voltage sources and things like that. So pretty much we're not going to have an ideal voltage source on chip, so we need to get rid of these guys here and this one here. Now, we also don't want to have a no connected to our output because we could have our output connected somewhere else. So we're going to get rid of this no connect block here. And now we can hold on to these VDD and ground connections because they're really just telling the circuit simulator and the software, they're pretty much just telling it that, okay, there does exist a VDD and a ground net, and they all need to be connected together, which is totally fine. We can definitely connect everything together on chip. It's just in the future we need to remember to power them if we're going to do any sort of simulation. Now, one thing that we'll notice here is if we tried to make a symbol, it's not going to work all that well because we don't have any pins. It doesn't know which net is the input, which net is the output, and if we tried to save and check, like we saw before, it's going to kick us back some errors. So what we need to do is we need to make pins that we can name in and out in order for us to make this symbol. So to make a pin, we can just press P. It'll bring up the pin menu over here. And what we can do is in names, we can start off by typing just in and placing it, but we can also type in and then space out. Now for our direction, we're going to use input output because that's just the most general. That's going to prevent any sort of issues later on. And then we are also, oh yeah, so that's going to be good for us right now. So now what we can do is we can see if I hover over here, I have this little hexagon that I can place. It says in next to it, so it tells us this is our input pin. I'm going to place it on the input where it's going to the gates. So I can click that here. Now we have another one that's output. So our in automatically deleted. Now we're placing the next one out. We could place it right here, but then our out is right over our line. So what we can do is come back to our menu, press this flip. Excuse me, this is flip. Which one is it? Flip horizontal. And then now we can place it right here on our output. So our pin menu is still up, but we don't have a pin name yet, so we can just press escape to get out of that. Now if we save and check, what we can see is that those warnings disappeared, so now our schematic's looking good. But typically, like if we're using an inverter, for example, and we want to pass a parameter up, if we just made a symbol right now, we wouldn't be able to really edit anything inside. We would have to dive back into the inverter and change something, which could be a little cumbersome. So if we wanted to pass a parameter up a level, so up into the symbol view, then what we can do, like if we were going to try and change our PMOS, we can click our PMOS, press Q, and then here for finger width, what we can do is that we can use P, lowercase p, and then capital P, A-R, and then open parentheses. And we can use colon, and we can just type in W here, and then close quotes, close parentheses, tab. We can see everything is kind of changed because now we have a variable defined here. But now we can just press enter. We can see that our width is now changed based off of this width, finger width, and that's going to, again, it's going to change a lot of things in the future, but the ppar command really lets us just pass that parameter up into the symbol. So we define it at the symbol level instead of having to define it at the transistor level. And hopefully that'll make more sense in just a moment. So let's go ahead and save and check one more time so we make sure we don't get any errors. So now if we want to make a symbol, Cadence has actually made it really easy for us to do that. So all we have to do is come up here to create, then highlight cell view, and then we're going to create a cell view from a cell view. So we have a schematic cell view. So we have a schematic cell view, so that's going to be our from, and then we're going to convert it to a symbol. So we're still going to have our schematic. It's not converting our schematic to a symbol, but it's creating a symbol based off of our schematic. And we're going to make sure it's named inverter so that it matches with our inverter schematic. Now we can just press OK. What's going to happen here is that a new window is going to pop up. So on the left side, we're going to have our input on the left side. On the right side, we're going to have out. So our input's coming in on the left, going out from the right side. Now for the top pins, we can just delete this. Bottom pins, we don't really care. And then everything else should be just fine. So now we can just press OK. Now here in just a moment, the symbol window is going to open, and this is going to be where we can edit the view, or edit, excuse me, the properties of our symbol and edit the shape of our symbol, because Cadence's default symbol is just a box. And it isn't super clear here that this is actually an inverter. So what we can do is we can press F to bring it to full screen. And now we can just kind of go around and delete a lot of these different components, right? Because we're going to make an inverter symbol ourselves, so we don't need this box. So we can delete a lot of different components from this box. So we can delete the box. We can hold on to this part name here because this is going to fill it in with inverter pretty much. And now for us to make an inverter symbol, we're going to need pretty much two shapes. We need a triangle and we need a circle to make an inverter. Now to make the triangle, we can just come up here to create and highlight shape. And what we're going to do is we're actually going to create a line. So we can make a triangle by just creating some lines. So I'm going to start up here in the very top, click, and then I don't have to hold. I can just release it and drag it down, and then click here where I want the line to stop. Now it'll form a line here. Now I can drag our line maybe a little further away over here, click it in the center, and same thing, drag it right back to where we started. And once I click here, it kind of closes that shape, and now we have our triangle. So we can see already that part name's probably not going to fit here pretty well. So what I can do is I can click it, I can press M to bring up the move command, and then click it one more time and just kind of drag it wherever I want. So I'm going to drag it just right here. Now we want to have a circle right here just to show that it is an inverter. So to do that, what we're going to do is go back to create. We're going to create another shape, except this time it's going to be a circle. So for the circle, we're going to have to start off clicking where we want the center to be, and then we drag it out to increase the radius. So we want the center to be right here where I have my mouse, and then I'm going to click, and I can drag out to make the circle with the radius that's about 2 grid lengths wide. And I can click, that'll make our circle. And then now all I have to do to finish this up is just, oops, that's the wrong thing. So I messed up, I drug this down when I shouldn't have, so I can either go back to edit and undo, or just press the U key. So what I'm going to do is I'm going to come over here, I'm going to select the pin and the out. So I just want to make sure that only those two are highlighted white, then press M, click one more time, and then I'm just going to drag this over here. So now our pin is connected to the edge of this circle, and then one more time I can click here. I don't want to click the circle, so I may have to click and drag. So I'm going to click down here. Oops, I messed up again. Maybe click that further down here. Just select our out. Let's see here. It's maybe tougher than I gave it credit for. Yep, so you pretty much maybe just have to move your mouse around until you can select only the out here. Then press M one more time. Move it to where it's maybe further back into the inductor, or excuse me, not inductor, inverter. So now this kind of helps make it look a little nicer. So we can do the same thing. Move instance name back here. And then for our bounding box, we can pretty much just select this side, drag it back over here. So now this has made our inverter symbol. So we can do the same thing, save and check. So if we've maybe forgot a pin or something like that, it'll give us a warning, but it's pretty much going to check and make sure that this symbol matches up to what we have in the schematic. So it has the correct number of pins, the properties match, and things like that. So now I'm just going to close this. I'm also going to close our inverter schematic. And then over here, what I'm going to do is now I'm going to make a new cell view, and I'm going to call this one inverter underscore TB for test bench. So this is where we're going to test our inverter. Now make sure it's schematic, can press OK. It's going to create this new schematic. And this new schematic is pretty much where we're going to be testing our inverter. So we can keep our inverter schematic pretty much exactly what we want it to look like on chip, where we have just 2 transistors. And then we can make our own cell view where we pretty much test our inverter, so we can have all those ideal voltage sources, things we can't realize on chip outside of it. So we're only testing our inverter. Now we need to add an instance, so I'll press I. And here, instead of selecting GPDK, I'm actually going to select AC tutorial lib, or whatever it is that you have whatever library you have your inductor in. Or excuse me, I keep saying inductor, whatever library you have your inverter in. For our cell, we're just going to click I and V, since that's what I named my inverter. And for our view, it should automatically populate as symbol. And now, that symbol that we made, I can just drag and drop this anywhere in our schematic. And you can see it automatically fills in the name inverter. It has an instance reference designator IO. And if we click this guy, press Q, we can see that that parameter that we passed W now exists in this symbol. So I can make one that's 120 nano here, because we need to make sure that it's defined. So I can define 120 nano here, press enter, and now we have pretty much our inverter in this test bench, and now we can add ideal voltage sources and things like that. So let's go ahead and add a voltage source. So that's going to be under analog library. So I'm using the instance window here. Now, instead of VDC, if I wanted to do a VDC or a DC simulation, we could use VDC. But for now, since we want to measure how the inverter responds to like a pulse up or a pulse down, we're going to use V pulse. Okay, and we're still going to use a symbol. You can see it makes a little square wave. So we're going to add this close to the input. Now we can also add a ground instance here. So I'll add one here. I'm also going to add one over here because I know we're going to need it later on. And then same thing, I'm going to add one over here for whatever it is we have at the output. So I can press W, go ahead and wire our input to the input pin of the inverter. Now on this output, instead of driving just nothing, and ideally this is going to drive like something like a capacitive load, so what I can do is I can stay under analog lib, can use cap, and then this is going to be like an ideal capacitor here. So now I can add our ideal capacitor right here, wire it up to our output. And this is going to be used for things like a delay simulation when we see how long it takes for our inverter to rise or fall. For our capacitor, I can just make it something, let's say I can make it something pretty small, like let's make it 1 femto for now. We can use that to see if it's realistic whenever we do our transient simulation. And then in a similar way, we still need something to power it on. So if we want to see what's inside this inverter, we can actually click on it, and we can go to View, Edit, Hierarchy, and then Descend Edit or Descend Read. So if we just want to look at it and not edit anything, we can just press E. And that'll open up this new window. We're just making sure we're opening it for read. We'll keep it in the current tab and press OK. And now this just shows us what our schematic looks like. So you can see here we have VDD and ground. If we don't have anything connected to those, the inverter's never going to turn on because it doesn't have power. So to get out of this, we can either click go up one level here, go up to the top, up one level and up to the top is the same thing. Or we could do Edit, Hierarchy, Return, Control E, or Return to Top. So for us, we can just press Control E, and that'll take us right back up here. So now I'm going to add a DC voltage source, VDC, symbol here, have one side connected to ground, and then bring up the instance window again. We're going to make a symbol VDD just to tell it that this voltage source is connected to VDD. And now I can click this, press Q, and let's just make this DC voltage VDD. Okay, so we can define it in the simulator what we want it to be. Now for our pulse, this can be slightly more complicated. Oops, excuse me. For our pulse, we can click on it, press Q. This may be slightly more complicated than a DC voltage source, so we can give it a DC voltage here. So I can go ahead and call it VN underscore DC. But what we really care about is this voltage 1 and voltage 2. So if we're going to have this going from 0 to 1, 0 to VDD, we can keep voltage 1 as 0, voltage 2 we can make VDD, and now it'll pulse from 0 volts all the way up to whatever we tell it VDD is. Now for the period, I like to use parameters here, so I'm going to use T, so T is pretty common for period. For delay time, we're going to do T divided by 2, so that's going to say it's going to be low for half a period, and then it'll be high for half a period. For our rise time, let's make it something pretty small. Let's make it like 100 pico for now. Fall time, we'll make it the same, 100 pico. Actually, we can define both of these as TR and TR. And then for our pulse width, we also want it to be T over 2. So it's going to pulse high for half a period, pulse low for half a period, which makes sense. And then for the type of rising and falling edge, let's just keep it as linear. So now I can just press enter here. And now, since we have pretty much everything defined, we have just double check and make sure that our width is actually defined here in this symbol. Now we can do what we did before and launch our simulator. So we can do launch ADEL. And then here, once it gets set up, make sure we have the license checked out here. So here what we can do is we can just do our regular setup, make sure everything's right. I can already see that it's set up to Spectre. We can change our model libraries to where we want to make sure we're using TT, the typical for our initial simulation. Apply and OK. Now for our analysis, instead of doing a DC analysis, what we want to do this time is a transient analysis. So for a transient analysis, what this is going to do is this is going to actually simulate versus time. So it's going to simulate for a certain amount of time and see how the inverter responds based off of the stimuli we've given it. So for our stop time, if we want to see 2 full periods, we can just make our stop time 2 times var open parentheses, open quotes, and then we define our period as T. So then I can close quotes, close parentheses, and then make sure we click enabled so that we actually do the simulation, and then press OK. So now we have our transient here. We can see it already defined us, or it already added a T here because we defined it up here. But if we copy the rest of our variables, we can now define our rise time. Let's set it 100 pico. VDD, we'll keep it 1 volt. VNDC, we can just give it a value, or excuse me, we don't want any DC value. We want to keep it as 0 for this simulation. And then for our T, let's do something like let's do something like 1 nano for now, 1 nanosecond. Well, we'll make it 10 nanoseconds for now. So for our first one, we'll do 10 nanoseconds. So now, if we set everything up correctly, we need to make sure we save and check our test bench, since that's what we're actually simulating. So it needs to be saved and checked. Now we can actually run the simulation, and we're going to let it run. We can check the CIW window just to make sure that things are actually progressing along. We haven't had any errors. So what we're going to do is we're just going to let the simulation run, and then after it runs, we'll touch base here again. We'll take a jump cut so you guys don't have to watch it run, and then we can take a look at the results. So I'll see you guys whenever this finishes simulating. Alrighty guys, so our transient simulation has finished. So what we're able to do here is that now we can go back to the results, direct plot, and main form. So we're still going to stick with main form. So it's going to open up a results window. It should be empty for now. And then it'll also open up our direct plot form here. So now for our analysis, we're going to stick with transient, and we're going to check the output voltage. And let's go ahead and add it to output. So we're still going to select the net on the schematic. For this one, we're going to care about this guy right here, our output. And then we can go back and see what our output looks like. So it's important to see what our output looks like relative to our input. So we can go ahead and check our input here as well. Go back to that window. And what we can see is that when our input is low, our output is high. And then same thing, when our input rises, our output begins to fall. Now for this, we did a very broad simulation, so it was kind of difficult to see what the rise and fall time is or what the delay is. So to change this, all we have to do now is go back to our simulator. We can change a couple of parameters here. So we can change, for example, Our period, we can drop it down to 1 nanosecond. We'll keep our DC low, our VDD 1. And then for our rise time, let's drop it down to 10 picoseconds. So since we dropped by a factor of 10 for our period, our rise time can drop by a factor of 10 as well. And then we can go ahead and resimulate. Now, the benefit of this is that now we don't have to, excuse me, now we don't have to actually look and see. We don't have to go back into our schematic and change those parameters manually. We can just do it from the simulation window, and that prevents us from having to save and check, do all that other really not fun stuff that can further complicate things. So defining things with the variables makes it very easy to change later on in the future, which is fairly important. Because you don't want to have to go back and change too much stuff. You want to be able to just change it in one spot, have those changes propagate throughout the entire design. So we can see it starting to simulate. We'll do kind of the same thing again. We'll touch base here once the simulation comes back, once it finishes. And then what we should see is that if we have this window open, those results should automatically change. So instead of it being 20 nanoseconds, now we should see that it is 2 nanoseconds. So we'll touch base here again whenever those results finish. Okay, so our simulation is finished up. What we can see is that because we already had this window open, it's pretty much just defaulted to this 20 nanosecond range. But we can use this slider up here to actually reduce the width of the window. So we can use that to kind of zoom in on what we care about a little bit more. Of course, if we close this window and then reopen it or rerun the simulation, then we're going to see the same results just kind of zoomed in like this. So what we can see is that with this rise time, now we can actually see the propagation delay slightly more. So the results from the inverter aren't going to be able to change as quickly as this input can. So now we can start to see a little bit more of this propagation delay and this rise and fall time in our inverter. Now, if we change this even more, or perhaps if we added more stages of inverters, then we would be able to see in more detail what's going on here. So this just gives you a little bit of an intro to the transient simulations, but I want to do something a little bit more robust. So what we're going to do now is we're going to actually change from just a simple inverter to something like a fanout 2. So I'm going to close this. We'll go ahead and save this state. So I'm going to save this state. We're going to save it as a cell view. Keep it here. So it's, like I said, it's a good idea to save your state. That way you have the most up-to-date stuff. We can close this guy now. We can also close this inverter test bench here. So what we're going to do is we'll make a new cell view. And this cell view, I'm just going to name FO2. And we want this FO2 to be a schematic. So we're going to stick with our schematic, press OK. Now, while we wait for the schematic window to load, what we're going to want from this fanout 2 inverter is going to be one inverter on the input, and then that is going to be driving 2 different inverters here. Now, compared to what we had previously, this will actually be much simpler for us to make because we don't have to manually assign all these transistors, change their values. We can actually just press I. We'll use the inverter symbol that we defined previously. And now for a fanout 2, we can just add one inverter here, and then 2 inverters down the line. So now all we have to do is just make our wired connections. So we can add a wire from here to our first inverter, from this net to our second inverter, potentially clean this up if you really wanted to. So here I could use something called the stretch tool. So press S. You need to press S, or maybe it's not S. So the hotkeys kind of change depending on, so it is M here. So M is the stretch tool in a weird way. So we'll press M. And we can just scoot this over so that now it's all in line. And then now we can also add a quick input line here. Oops, excuse me, didn't mean to right click. So quick input line here. An output line. So I think if you double click, that'll stop it. And another output line. Now, just like we did with the inverter, we're going to want to create a symbol from this. But we also want to make sure, too, that we define all the widths in this case. So for each of these, you don't actually have to press Q and open up this window. You can actually just use the sidebar right here. So for each of these, I'm just going to use 120 nano. And we just want to make sure 120 nano and 120 nano. We want to make sure that they all have something defined because otherwise the simulation is just going to break. Now we can do the same thing that we did before, add pins. So we're going to have one in. We're going to have one in and then out A, out B. Okay. So we can press hide here. We'll have our one in Now here, if we need to flip these around, we can just press F3 again to bring that menu up, flip it horizontally, and then add our out A and our out B. So now we should be able to save and check. Everything should work well. Don't get any errors. And now we can do the same thing we did before, create cell view from cell view. So we're going to create an FO2 symbol here. So we're making it sure it's from a schematic to a symbol. On the left-hand side, we're going to have in. On the right-hand side, we'll have out A and out B. And then we can just delete everything here. Press OK. And now a new symbol window should pop up with the same kind of default square that we can modify in order to make our fanout 2 symbol. So this is only if we really wanted to use the fanout 2 in a larger design, but this is, again, just better practice to figure out how we can make symbols here. So I'm going to start off just like how we did before. I'm going to just go ahead and get rid of this rectangle because it doesn't look all that great. Oops, that was the wrong one. Press U to bring that one back. Get rid of that green rectangle. And then what we can do is that we can use the same create, shape, and line. So I'm going to create an inverter symbol here. So we have our triangle made, and create shape, circle, make a circle on the end of it. And now, just to kind of make everything, we want our symbols to be representative of what's inside, I'm actually going to make 2 more inverter symbols. That's going to be for our out A and our out B. So I can move some of these things around just to get them a little out of the way. We can shift them back in the future if we want to. But for this, I'm going to move, oops, excuse me. So for this, I'm going to move everything a little out of the way just so I have room to kind of draw and create what it is that I need to. And I'm going to, again, not select that. So what I'm going to do is I'm going to try and figure out a way to not select this square. So I'm going to click, it may be easier if I just click our circle here, hold Shift, select all of these lines, and now I can press C, copy everything here, and we will move one of them. Let's see, we'll move it right here. Press C again, copy what we have selected. We'll move the other here. Control D. And now we can just create shape and line, and we can very, very easily make this fan out symbol. So I can double click there to stop the line tool, click here. And now our out A and out B pins, I'll move out A, excuse me. So we want to just select, let's press F, just select out A. We will move it over here to the top. Control D to deselect everything, and then I'm going to move out A over just slightly so that we can see it clearly. And then we'll do the same thing for out B. So out B, we'll move it here and move its label over slightly. I can see our pins are going a little bit over this bounding box, so we can just shift everything around a little bit. And since we have a little bit more space now, we can actually get everything nice and tightly packed in here. We don't want it to be too tightly packed or too cluttered or anything like that, so you can just kind of use your best judgment. So you can use your best judgment, figure out how you want everything to look. You definitely don't have to make it exactly how I'm making my symbol. You can take some creative liberties if you'd like. This is just the way I like to do things. So once we have this going, we can save it. So we save it, don't get any errors. We can go ahead and close this symbol here. Go ahead and close our schematic. And now I'm going to make a new cell view once again. That is FO2 test bench. And this FO2 test bench is really going to be where we can test this FO2 inverter. Okay, so we can start our FO2 test bench. I'll show you guys how to do a transient simulation with this guy again, just to kind of see how the results change and how things can be different whenever you have inverters driving inverters, how things can change here. So what we'll do is we will, like we did before, instead of bringing in an inverter symbol, we're going to bring in our FO2 symbol, FO2. So now we have just this symbol here. We can drag and drop right in the center of our schematic. Press F. And now if we look at this guy and press Q, we'll see that there's no parameters that we can change because we never used the ppar command in this schematic. So we used it in the lowest level, but if we wanted to continue passing it further and further up, we need to keep using the ppar command at every level. So now we can do just something very similar to the previous test bench we had. We will have, go back to analog lib, we'll have a VDC voltage source here for our power, because we still need power at every, we need power defined in every test bench. And then go back to our instance window. We'll add another V pulse. We'll add it right here to the input. And then for our outputs, let's see what happens if we drive a slightly larger capacitor. So we'll add a capacitor right here. So we'll use this fan out 2 pretty much in parallel to drive this capacitor, because this will kind of help to highlight how this inverter can be used in a real design. And now we need a bunch of grounds. So we can use our instance window again, put grounds everywhere that we need it, because if it's not grounded, the simulator has no idea how everything is connected, so we have to be very explicit. Same thing with VDD. We need to make sure we are powering the circuit. And that should be everything. Now we can just wire up every connection. So we can wire our input. We can wire these outputs together. So it looks like it doesn't like having it connected right here in the center, so this is just fine. Now we still need to define a lot of parameters. So here we can change this capacitance to, let's say, something like 20 femto, or we can be good designers and just use C out. So we can define it in the simulation window to see how the capacitance will change the results. For our V pulse, we're going to do something very similar to what we did previously. We're going to have, we'll keep our V and DC at 0 because we know we're not going to do any DC simulation. Voltage 1, voltage 2 will be VDD. Period, we'll keep it as T. Delay time, T over 2, or we could also just do TD. TR and TR for our rise and fall time. Pulse width, we want it T over 2. And then the rising edge linear. So you can apply this. And finally, all we have to change here is our DC voltage to VDD. Oh, excuse me, it looks like it kicked me out of that too early. So VDD, enter. Great. So now we have this schematic set up and ready to go with the simulator. So I'll press F. We have our schematic ready to go. A lot of variables defined. So now we can launch ADEL. Do the same thing that we've always done. We're going to go to the setup. Once everything finishes loading, we're going to change our model libraries. Make sure that we are using TT. So it looks like it's defaulting to MC. We want to use TT. Let's go ahead and copy over all of our design variables. So we can go ahead and define everything. Let's do C out as, well, let's say 10 femto. For our T, we'll keep it at 1 nano. For our T delay, let's say we want to have just 100 picoseconds of delay in the beginning. TR will keep 10 pico, and VDD will make it 1 volt. Okay. The only limitation we really have on VDD is that it can't exceed 1.1, or else the transistors will break according to the reference manual. So that's the only thing we have to do. We could use 1.1 here, but I'm just going to stick with 1. Now for our analyses, we're going to do same transient analysis. We want to see, let's just say we want to see T divided by 2. Okay, so we want to see T divided by 2. And we need to make sure we have this wrapped in a var, 2 times var T divided by 2. So I guess that would just be T. So var T divided by 2. So now we can just press OK. So it's going to simulate for 1/2 of a period. So it'll have a slight delay, and then we'll see the rise. And then we can actually see what the output looks like. Maybe we could even sweep T out to see what that ends up looking like with different variables. So let's go ahead and just run this really quickly to see, excuse me, to see what the output ends up looking like. Hopefully everything is working well, so we can check the CIW window to make sure everything is working. So it seems like it's getting through the netlist. Netlist generation failed because, if we scroll up a little more, specify online connectivity last updated. Looks like we forgot to save and check somewhere. So let's try saving and checking this guy. And then we can actually descend edit into here. And we can save and check. Go back up to the top. Make sure we just save and check one last time. And now let's check and see. Hopefully our simulation will now run. So we can check our CIW window. So it looks like it's getting a little bit further along. So it really is important to save and check at every increment, because if you don't save and check, the simulator won't even consider your design. So you have to make sure that it's saved and checked before you can run the simulation. So again, what we're going to do is I'm just going to wait for the simulation to finish, and I will talk to you guys whenever it is done. All right, so now that our simulation is finished, we can repeat the same process we've done before. Results, direct plot, and main form. Move our results window over here. And then for the direct plot form, whenever we finally get it, we're going to keep it as append, transient, voltage, add to outputs, and then we are going to look at the input versus the output. Okay. So now, because of the fact that we have two inverters essentially in series, whenever our input rises, our output will also rise here. So now what we can see is that we have a much more exaggerated rise time because of the fact that we're driving this capacitive load. And if we do something like a parametric analysis, we can actually see back to back what happens whenever we have like a larger capacitive load. So if I do tools from our simulation window, tools, parametric analysis, here for C out, so I'll pick the variable C out, and let's sweep it from 5 femto to 10 femto, and we just want 2 steps. Okay, so this will just allow us to kind of compare and contrast, see how the output capacitance can actually impact the delay. So we can go ahead and run these sweeps, and then we will monitor this and the CIW window just to make sure we don't have any errors. And then, like always, we'll wait for this to simulate, and then I will talk to you guys whenever it finishes. All right, guys, so the simulation has just finished, and we can already see in the results window that we have a couple of different things. So here on the left-hand side, we have just the input, and it's the same in both cases because it's well-defined. It's connected to an ideal voltage source. But what we can see is that the output does change depending on what the load capacitance is. So if we take a closer look at this, we can see that in the case where it's only 5 femtofarads, the output is able to rise considerably faster than the case where it is 10 femtofarads. So you can use this to kind of see how maybe different parameters could change the rise and fall times. You could use this to see how load capacitance change the fall times, how different numbers of inverters in the data path can change the speed of the data path itself. So this kind of gives you a lot of tools to be able to test and debug these circuits. So again, for what we did in this video is that we took a look at how we can create a symbol from a schematic to turn our schematics into something that's a little bit more intuitive to use. So instead of having to use two transistors for every inverter, we can just use an inverter symbol. We also learned how to pass parameters through a symbol so that we can edit the parameters inside of a symbol instead of having to go to the target schematic itself and edit parameters. We also saw how we can use the transient simulation with just a simple inverter and also with a fanout 2 inverter. So this should have given you some good practice on how to use symbols, how to do simulation, and this should give you a little bit more experience with doing these designs. You can definitely apply this to NAND gates, NOR gates, or even compound gates. Use this simulation to see how the different rise and fall times are affected by different parameters. So I hope you guys enjoyed it. I hope you guys learned something. If you have any questions or anything that you'd like me to address in the future, please feel free to either send me an email or leave a comment down below. More than happy to discuss that with you. Other than that, thank you guys for watching.